Well, sir, we are live now. We can start.
So, good evening, everybody. This is Dr. C.K. Ghosh speaking on behalf of IIPT Regional Council 15. This is the second edition of IIPT RC15's webinar on 100 years of quantum mechanics. We had the first edition last week, and we had two brilliant talks by Professor Ajay Kumar Ghatuk and Professor Bhubati Chakraborty. And today we have as speakers Professor Gour Das and Professor P.K. Aluwalia. The first talk is by Professor Gour Das from quantum mechanics to quantum materials. And the second talk will be by Professor P.K. Aluwalia. He will be speaking on a quantum material from the flat land of crystals, graphene. So we are looking forward to two very important talks on quantum material. In fact, this is the 100 years of quantum mechanics, and quoting from the most lucid and poetic popular science writer Carlo Rovelli, that the name of the book is Helgoland, the strange and beautiful story of quantum physics. And I'm just quoting one sentence. Nearly 100 years ago, on a windswept island called Helgoland, the young Heisenberg devised the theory of quantum mechanics. And it has transformed science. Since then, it has been a history. And I hope, and I sincerely believe, that the two speakers will enlighten us on this particular subject, which has revolutionized the understanding of physics and will dwell on the area of quantum materials. So I take this opportunity to welcome all the members of IIPT, all the listeners who have tuned in YouTube Live also. It is being streamed there. And in particular, Professor P.K. Aluwalia, the national president of IIPT. I particularly welcome Professor J.P. Das, but Professor Aluwalia will sort of introduce him to the audience. So it is over to Professor Aluwalia to introduce Professor J.P. Das.
Thank you very much, Professor Ghosh. First of all, let me welcome our very esteemed speaker today, Professor G.P. Das. And it's a privilege, in fact, to be with him today on the same platform. And he, in fact, requires no introduction. He's very well known throughout the country, internationally, and he is one of the very senior, most faces, a quantum scientist, material scientist, and a passionate teacher. And it's a great pleasure to introduce him today here for the audience. Professor G.P. Das is a condensed matter physicist who made important contributions in the field of first principle investigation of clusters, solids, and heterostructures, with specific application in material science and nano devices. He is a senior member of the computational material science community in India, with tenure spanning more than 4 decades as a senior scientist at BARC, Mumbai, as senior professor at IACS, that is Indian Association for Cultivation of Science, Kolkata, and IIT Kharagpur. Professor Das served as visiting scientist in Max Planck Institute for Solid State Research, Stuttgart, Germany, Virginia Commonwealth University, Richmond, USA, Institute of Materials Research, Sendai, Japan, and University of New South Wales, Australia. He is currently an emeritus professor at TCG Crest, Kolkata. Professor Das has authored and co-authored a large number of papers, review articles, and book chapters, and has also spearheaded important projects on spintonic materials, alloy thermodynamics, quantum structures, and sustainable energy. He is a fellow of the West Bengal Academy of Science and Technology and is a founding member of the Asian Consortium on Computational Material Science, ACCMS. Professor Das is recipient of several awards that includes MRSI Silver Jubilee Award and the ACCMS Award for high-level contributions to computational material science. Professor Das served as the president of IAPT Regional Council 15, that is West Bengal, Sikkim, and Andaman Nicobar during 2016-2021, and is well known for his flair in delivering pedagogic as well as popular lectures on physics of condensed matter. I am very happy to tell you also one thing, that he's a very warm personality. Once you will come in touch with him, he really infects you with the enthusiasm for physics and physics learning and physics research. I think we are privileged to have him with us in this year-long series, whose fifth version is actually going on right now. And I think it is a lecture of the 21st century, if I may put it like that, because we are talking about quantum materials all the time. There is a buzz of quantum materials around, not only in the country, but everywhere. Wherever you are talking, you are always hearing about, okay, if this technology is coming, there is a quantum material behind it. So we are looking forward to your great lecture, sir. Welcome once again. I also welcome the participants of this webinar who have found time to participate with us in this lecture. Thank you.
So before I pass it on to Professor G.P. Dash for his lecture, a small brief about his talk, as I have understood. Quantum materials encompasses the class of materials whose microscopic as well as macroscopic properties originate explicitly from quantum many-body effects. Graphene is the first Dirac material discovered in 2008 that manifests a plethora of superlative physical and chemical properties. I think we'll hear more about it from Professor P.K. Ahluwalia in the next talk. Most recently, wild semimetals with a pair of linear band dispersion and topological insulators with inverted band structure have been found to have some disruptive technological applications. In his talk, the speaker will give an overview about the emergence of quantum materials triggered by quantum mechanics. So we are feeling very eager to listen from a great scientist and a passionate teacher, Professor G.P. Dash. Over to you.
Thank you. Thank you very much, Professor Ghosh and Professor Ahluwalia, for your very kind words. Now, let me start by congratulating the IAPT RC15 for organizing this webinar series on 100 years of quantum mechanics, and also for giving me this opportunity to share with all the participants some of the historical recollections of the birth of quantum mechanics, followed by a century, nearly a century long discoveries of various very interesting things that part of which I'm going to cover. And all these led to what we today call quantum materials. So I will try in this 1-hour lecture to give you a kind of a flavor of the road from quantum mechanics to quantum materials. And that is the title of my talk. Okay. Let me start with the plan of my talk. So the plan of my talk is as the following. I'll start with some introductory remarks on early developments of 20th century. And then I will tell you about the roles played by statistics, symmetry, and topology. I'll start with a very simple example that the physics students as well as teachers start with in their quantum mechanics course, namely particle in a box. And then I will move over to what is known as the quantum adiabatic theorem, and also touch upon the concept of what is known as geometric phase in quantum physics. Then I'll come to Schrödinger to Dirac picture. The moving from Schrödinger picture to Dirac picture, where, as you all know, that quantum mechanics is coupled with special relativity. Then in the second half of my talk, I will tell you about how it is possible for us to tackle realistic materials using density functional theory, where the basic variable is not wave function, but electron density. I will just introduce it with a couple of slides without going into any details. And then I will come to the topology and the role of topology in condensed matter physics. That essentially started with the discovery of quantum Hall effect in the 80s. And of course, which all of us know, that it is graphene, which is the first Dirac material that was discovered in 2004 by Gaiman Novoselov. And I'm really glad that following my talk, there will be a detailed presentation by Professor Ahluwalia on this topic. And that is why I will purposely refrain from giving details about the graphene, which Professor Ahluwalia will mention. And then I'll conclude. So this is the plan of my talk. Okay, so essentially, I have kept this talk in a level which is a very general level without going into any technicalities for obvious reason, because there will be a heterogeneity in the audience, and that is why I've kept myself in that. Let's start with something which everybody knows. That is 4 remarkably simple relations that constituted the foundation of quantum physics in the 20th century. And all these 4 relations I don't have to tell you. That Planck's E equal to h nu, de Broglie's lambda equal to h by p, Heisenberg's uncertainty relation, and Einstein's E equal to mc square. Look at the one common thing, that is the simplicity of these equations. They are amazingly simple equations. So the world is being the sort of the quantum world is dictated by such simple equations. That is something to be noted. Now, when we go to the first quarter of 20th century, it is obvious that we have to start with the Max Planck's, discovery of the so-called the Planck's constant H, E equal to h nu. And this is the beginning of the quantum theory. But today, what I'm going to tell you is the transition from the old quantum theory to what we call quantum mechanics. Now, when we talk about quantum theory, the more general term that encompasses the overall field of studying subatomic particles and their behavior. It includes various approaches and theories related to quantum phenomena. When we talk about quantum mechanics, it is more specific term that refers to the mathematical laws and principles governing the behavior of subatomic particles. So we come to more quantification of these things. And these laws were developed in the 1920s, as you will see, by physicists like Erwin Schrödinger, Werner Heisenberg, and many others. And quantum mechanics is the application of these mathematical laws to describe and predict the behavior of quantum systems. So, in a very simplistic way, if we look at this table, on the left-hand side, I have told you the pillars which constituted quantum theory, starting with Planck, and then Einstein, and then Bohr, and then no other than our own Satyam Bose in the during this year 1900 to 1924. And this quantum theory, so what we also call old quantum theory, is a general field of studying subatomic particles, as I already told you. Now, on the right side of this table is quantum mechanics, which essentially started with Heisenberg, Wolfgang Pauli, Erwin Schrödinger, and de Broglie. And there we encounter specific mathematical laws and principles governing subatomic particles. And it focuses on mathematical descriptions and also predictions. Well, wait a bit. Is there some problem in the top? Can you see the top?
Yes, we can see, sir.
Okay, okay, fine. So let's see. When we talk about the transition from quantum theory to quantum mechanics, the two most relevant names that come up Number one, Werner Heisenberg in 1925, who came up with this amazing paper in Zeitschrift für Physik on which started what is known as the matrix mechanics. And I have just written that PQ minus QP equal to h by 2 pi I times 1. That 1 is actually a unit matrix. Remember that. And then in the following year, 1926, came Schrödinger's wave mechanics, which was published in Annalen der Physik, okay, in 1926 in a series of papers. And this equation is something which needs no mention. All of us know what is today called Schrödinger equation. One thing I would like to tell you, why is it that this is called the beginning of the so-called quantum mechanics? I use a quote, and this quote is taken from a Jagadish Mehra's CERN colloquium in 1976. He gave a fantastic colloquium on the birth of quantum mechanics. Now, look at this, what is written. Before 1925, people were working with Bohr orbits. Quite a lot of developments had been made about Bohr orbits. They provided a pretty satisfactory non-relativistic picture of atoms in which one electron was the important one. But there were great difficulties in understanding how two electrons would interact. Mark this, how two electrons would interact. The young people in these days were trying to account for the spectrum of helium by setting up a theory of interaction of Bohr orbits. And there is no doubt that they would have continued along the same lines if it had not been for Heisenberg and Schrödinger. They would have probably continued for decades. So there is a disruptive thing which happened in the history of quantum mechanics in 1925, and that is why we are celebrating 2025 as the the centenary or what is called the International Year of Quantum. Okay. This is a little bit of a history. In fact, it was also mentioned by Professor Ajay Ghatak in his beautiful lecture last week. I'm just repeating a part of it. It is a history. So following up de Broglie's idea, Peter Debye made an offhand comment that if particles behave as waves, they should satisfy some sort of a wave equation. Remember that this word wave equation was first uttered by no other than Peter Debye. And the man who picked up this idea and converted it to the most successful equation to describe the behavior of electrons was Erwin Schrödinger. His full name was Erwin Rudolf Joseph Alexander Schrödinger. Okay, now, as Felix Bloch recounts in his biographical memories, Peter Debye had said in Zurich in 1927, Schrödinger, you are not working right now on very important problems anyway. Why don't you tell us sometime about that thesis of de Broglie, which seems to have attracted some attention? And after Schrödinger gave the seminar, Debye dismissed it as childish, pointing out that to deal properly with waves, one had to have a wave function, which is not there anywhere in that simplest possible relation lambda equal to h by p. Okay, so there is no wave equation in that. So Debye was not happy. And that essentially put Schrödinger down, and he went for skiing holidays in Alps, as Felix Bloch recounts. And it is there that he came up with this equation, which is the most well-known today. Okay, the so-called Schrödinger wave equation, h psi equal to e psi. Well, once we have separated out the time dependence. Look at this. There is a spatial dependence and there is a time dependence. Okay, so if we separate out the spatial and the time dependence in this Schrödinger wave equation, we come up with what is known as the eigenvalue equation, which is called time-independent Schrödinger equation, and then we calculate the eigenstates and the eigenenergies. And this is how we set up the Schrödinger equation. Okay. Now the wave function, which is psi, which is written in the form phi times a e to the power I et divided by h slash. Here, remember one thing, that this en which is in the exponent, and this phi n, which is the eigenstate, this energy and the eigenstate should be having a one-to-one correspondence. So the energy should correspond to that eigenstate and they should match. Okay. And it is this factor which is known as the phase factor. And this phase is known as the dynamical phase. Remember this because I'm going to use this in the next couple of transparencies. So this phase factor which appears in Schrodinger equation is known as the dynamical phase. Now, this dynamical phase is a direct consequence of the system's time evolution, and it is distinct from what is known as geometric phase or Berry phase. And Berry phase is something which was discovered 50 years later by no other than, Michael Berry. And that paper is the beginning of another new era, which I will touch upon. Now, is that, is it really a myth or a reality? There are many people, especially the people who are not in the quantum physics, they sometimes, when they look at things like Schrodinger's cat, the Gedanken experiment or whatever you call it, that the cat is simultaneously dead and alive. The so-called Einstein-Podolsky-Rosen paradox, I do not want to go into the details at all, the Bell's inequality on which the Nobel Prize recently was given, and the so-called Bohr-Einstein debate and Einstein's famous quote that God does not play a dice. With all these things, some general common people may think that is quantum mechanics a myth? In fact, in this context, there is a fantastic article by David Marvin, which appeared in April 1985. The article is entitled, "Is the moon there when nobody looks at it?" So only when you do the measurement, then only according to the quantum theory, only when you do the measurement, then only you can observe it. So what is the reality? So the Marmin gives a beautiful, description of the quantum mechanics, where he says, is the moon there when nobody really looks at it? Okay. Is it a myth or is it a reality? Now, look at, for example, the atomic clocks, which are there in reality today. Okay. And we know what are atomic clocks, which gives us that up to 9th place of decimal accuracy in time. Okay. So the atomic clocks measure the frequency of light absorbed and emitted by atoms. And this is not a myth. This is a reality. And each tick of this clock is governed by the oscillations of the quantum superposition of electrons within these atoms, stimulated by the corresponding energy from a probing laser. So atomic clocks linked with the quantum level is the most accurate and stable than any other clock on Earth. Now, this is something which is a reality. So the debate whether it is a myth or reality is obvious to all of us. It is a reality. I would just touch upon, even though I will definitely not go into any details, that in those days of the first half of the 20th century, there were a number of interpretations of quantum mechanics that were given, and the most popular amongst those was what is known as the Copenhagen interpretation. Of course, it is followed, it is challenged by several stalwarts, and you can see in the list de Broglie-Bohm interpretation, many world interpretation, quantum decoherence, and so on and so forth, which will take definitely another lecture for me to cover. I would only try to tell you what exactly are the salient features of the Copenhagen interpretation in only one slide. So the principles of Copenhagen interpretation are as follows. A system is completely described by the wave function. If you know the wave function, you know everything about the system. Okay, this is what Schrodinger picture tells us. Then the description of nature is essentially probabilistic. Okay, with the probability of a given outcome of a measurement given by the square of the modulus of the psi. Okay, this is what is known as the Born rule, Max Born. Number 3, it is not possible to know the value of all the properties of the systems at the same time. And this is what is Heisenberg's uncertainty principle. I'll come to a little bit details in the next slide. Okay, and we all know about that. The Q and P are conjugate variable, E and T are conjugate variable. So, they all obey what is known as the Heisenberg's uncertainty principle. And number 4, what is known as the complementarity principle of Niels Bohr, that is, matter exhibits a wave-particle duality. An experiment can show that particle-like properties of matter or the wave-like properties. In some experiments, both of these complementary views must be invoked to explain the results. And so this complementarity principle in action is something which is also part of the Copenhagen interpretation. Finally, the Ehrenfest theorem, which we have read in our quantum mechanics book in our BSc days, there is a measuring device are essentially classical devices, and we measure only classical properties such as position and momentum. So the quantum mechanical expectation values, because these are all operators, so the expectation values of the operators, they obey essentially classical equations of motion, and that's a beautiful simple theorem known as Ehrenfest theorem. Finally, the quantum mechanical description of large systems will closely approximate the classical description, and this is what is known as the correspondence principle of Bohr and Heisenberg. So these are the 6 salient features. There are many more things. Those of you who are interested may go into the web and try to see the details of the Copenhagen interpretation, but these are the salient features of Copenhagen interpretation. Okay, I'll change the gear and I will tell you a little bit about statistics, symmetry, and topology, as I mentioned right in the beginning. Now, this is something where we slightly deviate from the quantum physics, but I think it is important for me to mention this. So the coming 2 slides will be essentially will be describing the role of statistics, symmetry, and topology. Okay, I'll start with this letter of Satyan Bose, which I think Professor Bhupati Chakraborty in his talk mentioned in some form or the other. So this is Bose's letter to Einstein in 1924 that essentially led to the Bose-Einstein statistics. So this is in German, okay? And in fact, Professor Chakraborty mentioned quite a lot of details which many of us did not know earlier. But look at the comment by Einstein at the bottom of that paper. He says, it is in English, although this part is in German, where he gave a derivation of the Planck's law. It's an absolutely fascinating and unique derivation of the Planck's theory of black body, okay, which was given by S.N. Bose, the most original derivation one can think of. And then Einstein says that Bose's derivation of Planck's formula appears to me to be an important step forward. The method used here gives also the quantum theory of an ideal gas, as I shall show elsewhere, Albert Einstein. So this is in the footnote of that paper of Bose's letter, and it is this which is, very, very important in the development of the quantum mechanics. I would also like to show you another letter, which is a letter written by Enrico Fermi to Paul Dirac in 1926. And that led to the so-called Fermi-Dirac statistics, okay? I don't want to read, but it essentially says, it brings into attention of Paul Dirac that I also, Enrico Fermi says that, a theory of ideal gas has been published by me at the beginning of 1926 in Zeitschrift für Physik, and he gives the reference. In those days there were no email, obviously. So he brings this to the attention of Dirac, and that is why today it is known as Fermi and Dirac both, Fermi-Dirac statistics. So why I mentioned about these 2 historically important letters, okay, that this essentially sowed the seed of what is today known as the quantum statistics. So we all know in the 19th century, the Maxwell-Boltzmann statistics, which is well known, e to the power minus E by kt, where k is the Boltzmann constant. Okay, the FBE is the Boltzmann distribution, and this is the Bose-Einstein distribution, whose expression is well known. FBE, Bose-Einstein, and the FD, which is the Fermi-Dirac distribution. In one case there is -1, and the other case it is +1. And essentially, it is these two distributions that encompass all the elementary particles that are known to us. So that way, the Bose's name is something which will never go out of the history, because 50% of the particles, as people say, are called bosons, whereas the remaining 50% are called fermions. Anyway, so that is as far as statistics is concerned. I'll tell you something about symmetry now. Now, whenever we are talking about symmetry, the first name that comes into the mind is that of Emmy Noether. Now, Emmy Noether is a German mathematician whose work essentially laid the foundation of the relationship between the conserved quantities and symmetry. So for every continuous symmetry of a Lagrangian, the Lagrangian is given here. This is a typical classical mechanics Lagrangian, as you all know. For every continuous symmetry of a Lagrangian, there is a conserved quantity. And she proved that rigorously. This is a profound concept which was introduced by Emmy Noether, demonstrating the connection between conservation laws and symmetries. And to be more explicit, here is a table. If it is a time translation symmetry, the energy is conserved. If it is spatial translation symmetry, the linear momentum is conserved. If it is rotational symmetry, the angular momentum is conserved. So this is something which is so fundamental for all the developments of the physics in the 20th century and later, that it in fact unifies. It is the most rich unifying principle of all physics, irrespective of whether we are talking about condensed matter physics or particle physics or astrophysics. Everywhere, the Noether's theorem is something which is valid. And that is why Einstein had a very famous quote. Einstein says in his obituary, by the way, Noether died at a very young age. You can see from 1882 to 1935. So at a very young age, she died. And she had a very checkered life. I do not want to go into the details. It is all available in the literature. But Einstein wrote in his obituary on Noether that she was one of the biggest creative genius of 20th century. Amazing lady. Okay. I will just talk about one particular symmetry, which is known as the time reversal symmetry in classical and quantum mechanics. Now, you may wonder as to why am I talking about the time reversal? Because later on, when I'm going to talk about the quantum materials, namely the topology, there the time reversal symmetry and inversion symmetry both play an extremely crucial role. Now, inversion symmetry, you all know from crystallography. Okay, what is inversion symmetry? But time reversal symmetry is something which is a little subtle. So what do you mean by that? That is, when you replace t by minus t, then what is the transformation that takes place? You can look at, for example, velocity. Now, when you apply the operator t, which is with a hat, on velocity and replace t by minus t, what will happen? The v will become minus v. So pictorially, it is written that it is something like as if you are rewinding your video. So if you rewind your video, then you will see that instead of this man going in the forward direction, it will be the man going in the backward direction. So this is what is known as the time reversal, okay, in classical mechanics. But the interesting thing is that in quantum mechanics, the similar relations hold under time reversal. And here I would like to point out a few things which is well known, but nevertheless, it is I think it is nice to recapitulate. Well, Q and P, which are canonically conjugate variable, obey uncertainty principle, which we all know. The commutation is IH/2. So if Q, under time reversal, what happens? Q, that is the position, remains Q, but momentum, which is the nothing but the velocity, it goes to minus p. So Q goes to Q, but P goes to minus p. So the commutation relation no longer holds. So how to solve this problem? So the similar thing you can try to see in T and E, which are also conjugate variable, because the commutation of T and E is IH/2. So E is the eigenvalue of the Hamiltonian. What about T? Now, remember one thing, that T is a parameter and not an eigenvalue of any Hermitian operator. This is something which we have learned in our early quantum mechanics books. And it was Wigner who first realized that in quantum mechanics, time, or rather than motion, reversal has to be defined in a very special way, different from all other symmetries. So time reversal operator is an anti-unitary operator. It maps I to minus I. And this is what is the relationship. And t square is 1. Okay. So then the canonical commutation relation QP will remain invariant under the time reversal. And consequently, this relationship is something which is valid. Now, those of you who are interested to have a rigorous derivation of this, the book by Sakurai on modern quantum theory is something which gives us this fantastic book. Okay. Finally, I would like to tell you something about, in this particular part of my digression, I'll tell about what is known as the symmetry breaking, extremely important in condensed matter physics. What is symmetry breaking? Okay, let me give you a Mickey Mouse diagram. Take a Mexican hat, as I have given here. Put a ball on the top of the hat. Now, obviously, when you put the ball on the top of the hat, this is the something which is symmetry. Obviously, it is a symmetric position. But is it stable? No, it is not stable. So it is an unstable equilibrium. And when the ball rolls down to this so-called this particular stable position, then this symmetry is broken. So unless the symmetry is broken, you are not getting a stable equilibrium. And this is something which is given here, that if we put a ball on the top of the hat, then the unstable equilibrium point, and under small perturbation, the ball would go downhill into the valley. Each point in the valley has the lowest potential energy. So it is a stable equilibrium. So you see, the symmetry has to be broken in order for you to think of or to explain, many phenomena in the phase transitions which we come across in condensed matter physics. I'll come up with that later when I come to topology. So now, with that digression, now I am back to quantum mechanics, back to Schrödinger picture. Okay. Now, Schrödinger equation can be exactly or analytically solved, as you all know, only for some specific systems. For example, particle in a box, which we do as a first chapter, problem in our physics teaching, okay, in quantum mechanics. So we all know what is a particle in a box. So the length of the box is L, and this is the wave function, and these are the energies. So this is the lowest energy, the second lowest energy, blah, blah, blah. And what is the width of the box? The width of the box is L. And this is something which is extremely simple for us to derive for the students. Fine. So far, so fine. Now comes something which is very interesting. Now, suppose I start changing the width of that box, which is L, slowly. So this is L at 0. That is at time t equal to 0. And then I start changing the width of the box from here to here. So the L0 to LT, if I do it adiabatically, what do you mean by adiabatically? That is, we turn it on at time t equal to 0 and turn it off at time t equal to t. Now, what is the meaning of adiabatic? Adiabatic means the time scale of the system's evolution is much shorter than the time scale of the changing Hamiltonian. Okay? Okay? So if we do it adiabatically, then what happens really? Will the same kind of a ground state wave function remain, or it will be different? Now, the stationary state of the quantum system immediately after the process of adiabatic length is turned off can be written as this. Look, the same good old Schrödinger equation, x comma t, with this L of t as a parameter. Okay, it's a parameter now because it's a function of time now. I'm changing the L from 0 to t. Then what will be the right hand side looking like? It will be looking like this xl e to the power I times integral 0 to t this. And what is this et prime on which you are integrating? That is given by the same, this one. At every stationary state, this is given by this, to pi xn divided by same thing. Okay, similar thing. So you are having the first thing is pi square h square, second one and so on. So the nth one is n square. So it is n square h square. Okay, fine. So you see, as you slowly expand the box, the E values will go like that. Okay. Okay. This is what was told by Max Born in 1928, Max Born and Vladimir Fock, as what is known as the quantum adiabatic theorem, an extremely important theorem, quantum adiabatic theorem. What is that? In a simplest way, this is not exactly what Max Born said in German, but it is here, it is written in English. A ground state system will remain in the ground state before and after the adiabatic change of the Hamiltonian without making transition to the excited state. Do you understand? So what happens is that this particular ground state wave function, which looks like this, okay, will remain. So from here to here, it will become. It will just follow from here to here. Now, this is what is the quantum adiabatic theorem. Very, very important. Now, what happens that a system which is in a state n, what happens to the Hamiltonian under the adiabatic process? So this is something which I have just tried to give you a pictorial view of what happens when you change from L0 to L1 to L2. Look, the same thing, it remains. So it is still remaining in the ground state when you are changing the width of the thing. However, it has to be done adiabatically. So this is where comes the expression for the wave function, where over and above what is known as the dynamical phase, which is e to the power it divided by h slash. You remember I had told you earlier, okay, in Schrodinger equation, there is another, phase factor which comes, and this second phase is called the geometric phase. So the first one, which is well known to us in our good old college days, that is the dynamical phase. But over and above that, there is something which is called geometric phase, where the parameter, in this case it is L, that is the width of the one-dimensional box. That is what is the parameter in this Schrodinger equation. Okay, so remember that we have got two different phases. One is called dynamical phase and that is called geometric phase. Okay, so how do you look at the Schrodinger equation where both dynamical phase and geometric phase are present? Okay, we invoke what is known as the Born-Oppenheimer approximation, which we all know, and there the coordinate RT of the nuclei are regarded as a parameter. Those of you who do a little bit of electronic structure calculations, you know that when we solve the Schrodinger equation, we solve the, we take variable as the electronic coordinate small r, and the ionic coordinate capital R are kept as not variable but parameter. Okay, so small r, which is the electronic coordinate, is a variable. Capital R is a parameter of the nuclei. So now my parameter, earlier I was telling you the parameter is L, that is the length of the box. And now, the when we try to solve a problem like a hydrogen atom problem or helium or whatever, there we have got both the electronic coordinates and the ionic coordinates. So the ionic coordinate is considered as a parameter, and the quantum states of the electrons are slaved. What do you mean by slaved? That means they follow like a ether drag along with the ions. Okay, so when R moves, the electrons, they follow that. So that is why it is called slaved. So we usually try to solve the time independent Schrodinger equation, where this theta is nothing but Et by h slash, which I already told you, the dynamical phase. Okay, and when we go to the time dependent case, then as I told you that over and above this I theta nt, we have got I gamma nt, and this I gamma nt is something which is given by we use expression. Don't worry about how the expression we have got, but this is something which is well known to us in the quantum mechanics, but this is not that well known, and this is this gamma nt, which is known as the Berry phase or the Berry curvature. Okay, and choosing a suitable gauge transformation, this is a matter of details. Let us not go into that. The theta n, that is the dynamical phase, can be vanished, but not the geometric phase gamma n. So gamma n geometric phase will remain. And this is the famous paper in 1984, which is known as the quantal phase factors accompanying adiabatic changes. This is what is today called Berry phase. Okay. Now, a little bit of illustration of Berry phase. Those of you who know Foucault's pendulum, I'm sure you have seen. I mean, in Ayuka in Pune or in our parliament house in Delhi, we have got Foucault's pendulum, and you know Foucault's pendulum, which precedes in 24 hours, which all of you know. Now this is called parallel transport. Okay. And it was Michael Berry who first showed that the concept of parallel transport can also be applied to quantum mechanical states when it makes a loop in the parameter space. What does it mean? That means you start from here. Okay. Let's say from here you start, you go like that, go along this, come back, the phase changes. You see, here, when you are going like that, the phase was this, and when you go like that, the phase changes. So this change in phase is something which is related to geometric phase or the Berry phase. It is a matter of details how it is possible for us to find out the solid angle, which requires a little bit of algebra. Okay, spherical geometry it needs. Let's not go into that. So without going into any mathematics, what is the difference between the dynamical phase versus geometric phase? In a very simple term, the dynamical phase describes the oscillations that occur even if the parameter does not change. That is the e to the power I omega t, which is well known to us. And the geometric phase describes an additional phase from the changing of the parameters. In this case, it is r of t, that is or it is L, or whatever be the parameter for that particular system on which you are solving the Schrodinger equation. So after one cycle, see, you make a full cycle and you are changing the phase. Okay. After a full cycle, the dynamical phase answers the question, how long did your trip take? The dynamical phase. Whereas the geometric phase answers the question, where have you been? That is the most non-mathematical way of separating out the dynamical phase and the geometric phase. Now I come to the second part of my talk. May I ask Professor Ahluwalia or Professor Ghosh as to how much time can I take now? Can you please tell me how much time I can take now?
As per the schedule, you have another 10 minutes.
Okay.
We can extend it up to another 15 minutes. Say.
Okay, fine. Fantastic. Okay. Now let's talk about now we come to the materials. Now, the moment we talk about materials, we talk about periodic table, which is, so how to understand materials in the periodic table. All of us know about hydrogen atom problem. This is something which is in the textbook. Okay, where we know what is the shape of the potential. Okay, it is a Coulomb potential E square by R with some prefactor, and we solve the Schrodinger equation. Okay, this is and separate it out into radial part and angular part, and we arrive at this famous expression which is there in the first year textbook. Okay, En equal to this proportional to 1 by n square. So each wave function will depend on the quantum number n, L, ml, ms. And it was Max Born, 1926, who rigorously interpreted mod chi square as the probability density of finding an electron at position x and time t. Now, question is, the periodic table is beyond hydrogen. And whenever you go beyond hydrogen, it is not a one electron system. It is more than one electron system. It is called many electron system. So we have to solve what is H chi equal to E chi, where chi is essentially a function of R1, R2 up to Rn. And what is n? N is of the order of 10 to the power 23, which is Avogadro number. So it's a humongously complicated wave function. So how to solve the Schrodinger equation for elements in the periodic table beyond hydrogen atom? That is, elements having 2 or more electrons in presence of nuclei. 3 things are important. Indistinguishability of electrons. As you know, you cannot distinguish between electron number 1 and electron number 2. Coupled with the fermionic nature, which we also know it is half integral spins. that lead to the so-called antisymmetric requirement. And with exchange, when you exchange two electrons, there is an antisymmetry requirement, and that is what led Slater to come up with what is known as the determinantal wave function. Automatically, in a determinant, you have got the antisymmetry built in. So Pauli exclusion principle ensures that no two electrons can have the same quantum states and that is what is important for understanding the materials in the periodic table. Now, what happened? There was a lot which happened during the 50 years in the last century after the quantum mechanics until maybe about 1960s or something like that. The Schrodinger equation for many electron system people tried to solve. Many electron system means atoms, molecules, and solids. And they can't be solved exactly. And one must invoke approximations. So you cannot solve it analytically when you go beyond one electron. And the approximations are, for example, Born-Oppenheimer approximation, mean field approximation, pseudo-potential approximation, linear combination of atomic, and so on and so forth, all of which have been well developed since 1930s in the post-quantum mechanical era. Okay? The most efficient and widely used approach to solve the n-electron problem is what is known as the density functional theory. And this was formulated by Walter Kohn in 1964-65, exactly 35 years after the, 35 to 40 years after the quantum mechanics was set in. Okay. So in DFT, or density functional theory, in short, it is called DFT. The electron density is the basic variable. What is electron density? It is minus E multiplied by the probability, mod chi square. It is and remember that n of R is a function of only three variables, x, y, and z. And that plays a central role instead of a many electron wave function psi, which is a function of 10 to the power 23 variable. So this simplification is amazing. Instead of handling a 10 to the power 23 variable system, we are handling a three variable system in n of R. So we are going to talk a little bit about this part, namely the density functional theory. In this context, I remember Dirac's quote when he said in the 1928 that the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws lead to equations that are too complicated to be solved. So he mentions how the many electron equation looks like, and how a Schrodinger equation, and how difficult it is to solve it. That challenge was really taken by no other than Walter Kohn 35 years later. Okay, and this is in one glance what is density functional theory. It's a quantum mechanical modeling used in physics and chemistry to investigate electronic structure of many body systems. Whether it is atoms or molecules or crystals or clusters, whatever. Essentially, what you do is that a true many electron problem is mapped onto a self-consistent one electron equation. So original problem is interacting, but we map it onto a non-interacting, easy to solve equation, which is known as the Kohn-Sham equation. And again, without going into any technicalities, you know from Schrodinger equation that in the Schrodinger equation, if you know the potential, you can solve the Schrodinger equation and get the wave function. And from the mod chi square, you can get the charge density. This is the conventional wisdom. But Kohn-Sham theorem, or the density functional theory, the first theorem in 1964 by Hohenberg and Kohn, that says exactly the opposite. That is, if you know rho of R, you can uniquely predict V of R. So instead of going like that, you are going just the opposite. You know rho of R, and you can exactly predict V of R. Here, I would like to tell you about, I remember when I told you about the Copenhagen interpretation, I told you that it is a psi of R. If you know that, you know everything about the system. It is a density functional theory which enormously simplified the entire scenario, and they said, if you know rho of R, the density, which is a function of three variables, then you know everything about the system. That's an enormous simplification. So basically, you go from wave function to electron density. Okay, so this is a matter of details, how we solve it. The only thing which I would like to tell you is that the Kohn-Sham equation is exactly like a Schrodinger equation. Look, this is the kinetic energy. In the right kind of a H slash curve by 2m is taken as 1. So kinetic energy, and these three are the potential energies. So kinetic energy and potential energy is a total Hamiltonian. Operating on phi is epsilon I phi. So you solve it and you get what is known as a total energy functional, where there is a kinetic energy term, then there is an external potential term, there is the electron-electron term, and there is the exchange correlation term. And this is something which is probably today the most widely used approach taken by people who are working in materials physics and chemistry. Okay. Now I will tell you, whatever time is left for me, I will tell you how we transit from our current understanding of materials in 20th century to the wherever we have arrived at 21st century. So in 20th century physics, whatever we understand, we know we can explain the behavior of a metal, an insulator having a large band gap, a semiconductor having a smaller band gap like silicon, or a semi-metal where the conduction band and the valence band, they just touch. Now in 21st century, what happened is that apart from the normal band structure, we have got the band crossing here, which is at the critical point, instead of being a parabola, which we teach to our students in our electronics book, it is not a parabola, it is a straight line. So you see the conduction band and the valence band, they meet at a particular point, which is called a Dirac point, okay? And further to that, there is something which is called the inverted band structure, where you have got the valence band and the conduction band, instead of going like that and like this, it is inverted. And that is something which is dictated by three things. Again, statistics, symmetry, and topology. So I don't know whether I will be getting any time to tell you more about the topology, probably not. But anyway, I'll at least try to give you the flavor. So some of the basic concepts is something which I can skip because these are well known. So when you are talking about a massive particle like electron, you are having the energy versus momentum as like that. And when you have got a massless particle like a photon, the mass is 0. So E is proportional to P, square root of Cp square. So Cp. So it is a straight line instead of a parabola. Okay. So Paul Dirac was the one who combined quantum mechanics and special relativity and arrived at what is known as the Dirac equation instead of the Schrodinger equation. So again, this is textbook, so I do not want to tell you. I can jolly well skip it. From Schrodinger equation, but only thing which I would like to tell you is the Schrodinger equation is first order in time and second order in spatial coordinate. From there, we come to Klein-Gordon equation, which is second order in both time and spatial coordinate. Now, Dirac looked for an alternative which was first order all throughout. So you see, this is first order in t, second order in x. Here, it is second order both in t and x. Here, it is first order all throughout. And this has got an absolutely amazing effect or influence on the later development in quantum mechanics. And you can write the Dirac equation in terms of what is this kind of an equation, which is, of course, from the Dirac equation, you can derive Klein-Gordon equation if you just, square it. You just square it, you get Klein-Gordon equation, but not the other way around. Okay? So Dirac, with his genius, he introduced what is known as the Dirac matrices, which is again well known. These four Dirac or Pauli spin matrices. Okay, and there is a quote. Niels Bohr once asked, "What are you working on, Mr. Dirac?" And Dirac said, "I'm trying to take square root of something." Now it is only a mathematical physicist like Dirac who could do the square root of this quantity without taking a square root. When I ask you to take the square root of 4, you have to do it. If I ask you to square root of 3, you have to work it out. But Dirac did not take the square root, did not work it out. He just wrote it as a linear combination of sigma x, sigma y, and sigma z, the so-called Pauli spin matrices. And that is something which is the mathematical genius of Dirac, which ultimately led to what is known as the Dirac equation. So this is the Dirac equation. Okay. And well, that is what ultimately, as you all know, led to the particle and antiparticle, which metamorphosed the entire picture of particle physics in the second half of the 20th century. Now, there are remarkable outcomes of Dirac equation. I will skip these things because of lack of time. So just I would like to tell you that this is the Schrödinger picture, where H equal to written as a p square by 2m as a parabola, and this is where is an ultra relativistic Dirac particle, where it is a linear relationship. And when you go from a massive particle to a massless particle, all that you replace is the same equation, only the velocity of light is replaced by the group velocity of the electrons, VF. Okay, that's it, which is of the order of 10 to the power 8, about 2 orders of magnitude less than the velocity of light. Okay, now I will have to finish off things. I already told you that from semiconductor physics, where you have got parabola, when you come to this kind of a linear dispersion, and that is what is seen in graphene, okay, where E is proportional to P, whereas here E was proportional to P square. And it is this which is the simplest Dirac material in action, and that is graphene. And this is where Professor Aluwalia will give you the details, and I will skip these things, okay? So it is a two-dimensional monolayer of carbon, and many more things he will learn in his talk. Note one thing. There is a confusion among some of the students. Electrons moving in the special environment of graphene lead to some special effect that they behave as if they are massless. Electrons are not massless, but they behave in such a way because the effective mass is something which is related to the derivative of this dispersion. So derivative is 0 because it is a straight line. So it behaves as if it is massless, and they obey Dirac equation. So now, in 21st century, I'll take Professor Ghosh. I will take maybe about a couple of more minutes. That's all. So in 21st century physics, there are a lot of happenings which are absolutely exciting, starting from the discovery of graphene in 2004, and then there are a lot of Dirac materials. Okay. There is what is known as the quantum particle zoo. These are Dirac materials, Dirac fermions, Weil fermions, Majorana fermions. These are so exciting that today a large number of groups all over the world are working on this, and it follows many other things like anomalous Hall effect, topological orders, twistronics, spintronics, and blah blah blah. This I have to tell you that what exactly is the turning point from 20th century physics to 21st century physics. This is something which I must tell, especially for the younger students. It was 1980, that is von Klitzing's discovery of quantum Hall effect, that marks the advent of topology in condensed matter physics. Okay, because in condensed matter physics, it is commonly observed that an ordered state at low temperature undergoes a phase transition when a symmetry is broken. I told you about the symmetry breaking in the beginning of my talk. For example, when ferromagnets break the symmetry of a paramagnet. This is a paramagnet. This is symmetric. He is ferromagnet. This is not symmetric. This is in only one direction, all the spins. So symmetry is broken. This is the pre-1980 view of quantum mechanics. Now, what about the post-1980 view? Subsequently, it was found that there are types of order which occurs where it is not necessary for the symmetry to be broken. I cannot go into the details, but the integral quantum Hall effect, which is observed by von Klitzing in 1980 in Max Planck Institute. Actually, it was the experiment was done in Grenoble. Okay, and that is where I spent quite some amount of time in Germany. So I remember my interactions with this group who are involved with the quantum Hall effect in Max Planck Institute. And well, today it is well known that the topological order, for example, the plateaus in the Hall resistance are exactly coming at integral multiples, and these are integral means this is of the order n times e square by h. E square by h is a fundamental constant, and n is an integer, means it is integer. It is up to 10 to the power minus 9. So it is not 0.999. It is 0. up to 9 nines. the accuracy, amazing. And that is only possible if there is a topological order. And of course, after 1980, the thing which really hammered our idea of the quantum materials and the topological materials is graphene, which is the first Dirac material. Okay, so I will skip all these things. Okay, this also topology. I will skip these things and just come to the final. These things. Yeah, the quantum materials. So. The last slide, the quantum materials, the materials exhibiting exciting physical properties dominated by quantum mechanical effect. So this can have a large number of things like quantum fluctuations, quantum entanglement, quantum coherence, topological behavior, and so on and so forth. I only discussed only one thing, namely the topological materials, and more you will hear in graphene. So this starting from quantum Hall effect, there are so many which are developments in 1980s, 90s to present and to future. Okay. So this is something which I have obviously I have taken from the Google. See the emerging world of quantum materials, and this is truly exciting. Topological insulator, Dirac semimetals, wild semimetals, and so on, new fermions, and so on and so forth. And all these things are flooding the quantum materials scenario today. Here I have given some recent review articles which are all, you see, 1920s. This is 2021 by Claudia Felser, 2022, 23, 25. So these are all the reviews which are written by different groups in the last 5 years. Okay. And the history is also given. This is also from one of the reviews in 2025, 1980s to 90s, to present to future. Where are the quantum materials going, and what are the properties? Okay, the quantum confinement, the strong electron correlation, and what I told you about topology and symmetry. Okay, so the conclusion. What have I discussed in this talk? The quantum mechanics from 20th century to the quantum materials in 21st century. The role of statistics, symmetry, and topology. Very, very crucial role they all play. I mentioned about the dynamical phase versus geometric phase, or what is also called Berry phase. Okay. Achha. Then density functional theory is the established workhorse for exploring many electron system. Okay. How to solve many electron system. Density functional theory is the unchallenged workhorse today. Then I mentioned about the quantum Hall effect, which marks a paradigm shift in our understanding of condensed matter physics. And of course, graphene, the first Dirac material in the flatland. So we are entering really a new emerging world of topological materials with intriguing and hitherto unknown properties. This is a fantastic picture, a rare picture of, of Dirac, Heisenberg, and Schrödinger with the three ladies. The first lady is, Heisenberg's mother, not wife. She is Heisenberg's mother. She is Dirac's mother. And this is Schrödinger's wife. And this picture is taken in during the Nobel Prize ceremony. As you know, that 1932 Nobel Prize was won by Heisenberg, and 1933 by Schrödinger. And later on by Dirac. So all these three Nobel laureates, who are the architects of the quantum mechanics, which is given here, this photo. And the mutual admiration, you see, Paul Dirac told about Heisenberg. I have the best of reasons for being an admirer of Werner Heisenberg. He and I were young research students at the same time, about the same age. They were born in 2001 and 2002, respectively. Okay. And got the Nobel Prize in 1932 and 1933, respectively. Paul Dirac a little later. Okay. He and I were young researchers about the same age, working on the same problem. Heisenberg succeeded where I failed. This is what is told by Paul Dirac. Imagine. There was a large mass of spectroscopic data accumulated at that time, and Heisenberg found out the proper way of handling it. In doing so, he started the golden age in theoretical physics, and for a few years after that, it was easy for any second-rate student to do the first-rate work. you can imagine whom he mentions about the second-rate student. Anyway, now look how Werner Heisenberg reciprocated on Paul Dirac. Heisenberg says on Dirac, I think that the discovery of antimatter was perhaps the biggest jump of all big jumps in physics of our century. It was a discovery of utmost importance because it changed our whole picture of matter. So I think that is where I stop, but with a quote by P.V. Ramakrishnan, our own, the senior most condensed matter physicist of our country. He writes in his Journey in Condensed Matter Physics, which got published here, a special issue, okay, on Anderson localization. He says, the flowering of topology in condensed matter physics is another source of joy and wonder. But most of all, it is the unfailing regularity with which unexpected major experimental discoveries continue to be made in condensed matter physics that convinces me that the end of science, certainly of this particular subfield, is not near. Thank you.
Thank you, Professor Dash, for your very illuminating talk. I can understand that time had been a constraint. The parameter time became your constraint, which was effectively a part of your lecture also.
But Professor Ghosh, I would like to say that I checked at my watch. I think I started exactly an hour back, right? I think so. 6:45 I started and it is 7:45 now. But anyway, doesn't matter. Yeah, okay.
Actually, we have another talk, and
yeah,
the entire schedule is up to 8:45. We may have to extend that.
Yeah.
No, nothing to be sorry about. It was very interesting. We would love to have it continued, and so that you could have given the whole gamut of your experience, which you could not because of the constraint of time. And I think I know there are many questions in the mind of the audience. We may take one or two so that the next lecture does not get delayed. So let me check the chat box also.
I think there is a hand which has been raised by Professor Ahluwalia.
Yeah. So thank you very much for a wonderful talk.
Thank you.
And the way you really, there were many peaks in the talk, if I may say like that. And it was a master class which you presented today. I think it was full of knowledge. And I think you touched upon such personalities about which I think people do not know that what they have done. For example, Noether was one personality which you talked about. Then berry phases, normally we are never going to talk about that even in postgraduate classes. We just don't really talk about it. Yeah. Focus on time inversion was a wonderful way to look at it. And I think this Cohen's story is the story of the last 50 years, which blossomed into what we are seeing in quantum mechanics today. I think everybody is doing it. It's like a kind of as you said it perfectly, that it's a workhorse of doing quantum mechanics itself today, particularly focusing on material science itself.
Yeah.
And I think you found time despite your very, very busy schedule. IEPT expresses its gratitude to you. Thank you very much.
It was a pleasure. Thank you so much for all your kind words, Professor Ahluwalia. And I'm looking forward to your talk.
Yeah. Another interesting peak was your reference to Foucault's pendulum. That was very interesting. Incidentally, Noether's theorem and Einstein's general theory of relativity, they both came in 1915.
Yes, exactly.
So I request every other person, every other member of the audience who would be having some question to interact with Professor G.P. Dash through his email account. Is it possible?
Yeah, sure. I have given the email already in the beginning. That can also be shared. Did I give the? I think I gave the. Let me just check. I think I gave the email.
You can quickly read it out.
Yeah, I think I gave the email. Yeah, here it is.
Oh, okay.
Yeah. So this is my official email account. So anybody who is interested can send me any query whatsoever to my this is the account in my TCG Crest account. So you are most welcome, anybody to send me. Yeah.
So in spite of all of our desire to have it continued, we have to stop somewhere. And here we are stopping as we have to go through the lecture of Professor P.K. Ahluwalia.
Yeah.
And before
should I
you must stop. You must stop sharing the
yeah.
screen.
I'm just doing that. Give me a second.
So before we switch over to the next talk, I once again thank Professor G.P. Dash for this brilliant talk on quantum mechanics to quantum materials. Our next talk is by Professor P.K. Ahluwalia. It is on quantum material from the flat land of crystals, graphene. You have already got the indication that was given by Professor G.P. Dash about the subject matter of the talk by Professor P.K. Ahluwalia. So before I give a brief about his talk, let me have the privilege of introducing Professor P.K. Ahluwalia to you. In fact, like Professor G.P. Dash, Professor Ahluwalia had the privilege of introducing him. I feel myself privileged in introducing Professor P.K. Ahluwalia. He has many feathers in his cap, and the list of credentials is indeed too long. I have cut short it by some extent, of course, without taking the permission of Professor Ahluwalia. So I'm telling the salient features of his credentials. He has inter alia held several positions. Prime among them, he was a professor of physics at Himachal Pradesh University. He was member HP State Higher Education Council. He was the Dean Faculty of Physical Science during 2011 to 2013. He was the Director of International Quality Assurance Cell of the university during 2011 to 2014. He was the Director of University Institute of Information Technology from 2000 to 2008, and he had been the member of Academic Council, Himachal Pradesh University, since 1980. So these are few things which I can mention about his teaching career. And then he has been a great researcher. And it's a twofold from the broadly, you can divide his research interest into two-pronged issues. One is condensed matter physics, and another is physics education research. In fact, I had the privilege of discussing with him on several points on physics education research. He has guided 18 PhD students and 34 MPhil students. He has 3 books on computational physics and related areas. And most importantly, he has created many facilities for research and related areas in HP University. He has more than 120 research publications in peer-reviewed journals with a very high degree of citation. As regards award, he is the winner of Commonwealth Academic Fellowship at the University of Edinburgh during 1997 to 98. He got the Best Teacher and Academic Administrator Award by HP University 2012. He got the Environmental Leadership Award by HP University 2017. He had taken many significant on-campus initiatives. I'm not reading them out now. He had been a science popularizer, a very passionate science popularizer. Like Professor G.P. Dash, in fact, we have 2 speakers today who have the same kind of approach towards their career. One part is research and another part is disseminating research by their passionate way of teaching. And in spite of all these things, in spite of all this busy schedule, well, Professor Ahluwalia has a tremendous passion for sketching and drawing. And then Simplicity is a hallmark. He does it mostly with pencil. We keep receiving such drawing. And for us, what is most important, that he is the national president of Indian Association of Physics Teachers. So this is Professor P.K. Ahluwalia for you. I had just cut short his introduction, but I had to do that for the constraints of time. And I'll quickly go through a brief about his talk. Professor Ahluwalia will be taking us on a fascinating journey into the world of graphene, a revolutionary two-dimensional crystal that is redefining the boundaries of material science. Discovered in 2004 through a serendipitous experiment with graphite and Scotch tape, graphene has unveiled a treasure trove of amazing properties, inspiring on intensive search for more two-dimensional crystals. The talk will explore the mind-boggling applications of graphene as a quantum material, showcasing its potential to transform industries and push the frontiers of innovation. So that is most crucial about graphene, where we can have the confluence of research and industry. So without taking much more time, I take you over to Professor Ahluwalia, where we will be awaiting his talk. Professor Ahluwalia, please.
Thank you very much, Professor Ghosh. And it's my good fortune that I am today. I heard a wonderful talk. It was a treat, I would say. And this Professor Das gave us what you can call as a very big eye view of the quantum mechanics influence in the last 100 years. I'm just going to pick out first, uh, chapter of the wonderful things which happened in the beginning of this century itself. And I think, if I may say, the graphene is the queen of that particular kind of a idea which I am going to share with you. There is a reason that I have picked up this talk, and I think uh, the reason is that many a times people ask very often that, okay, we are celebrating quantum mechanics 100 years. Can you come and give a talk to students, maybe studying in a school, and can you make them appreciate, after all, what is going on here in this uh, what you can call as area? And I believe that the best part of this is that if we can really bring down all those complexity before the students and make them appreciate and excite them about what is going to happen in, say, next 50 years because of the quantum mechanics itself. And a case study of that is, in fact, graphene itself. I have not really, I'm not going to give you any, a kind of a outline of the talk, but it will flow automatically in a very, very simple fashion. This first picture, which you are seeing here on the screen, is taken from that first paper which was published with the discovery of the graphene itself. And we know that it is because of just one element in the periodic table, which is a wonder element. And I think any school student knows about carbon. Every day, a student uses carbon in the form of a pencil with which he or she writes on copy. And I think nobody wondered that when we are writing it, we are actually printing nothing but a two-dimensional allotropic form of carbon on the paper itself. But what we get right in the very beginning of the introduction to carbon is through what we call organic chemistry. And it also transcends beyond chemistry into biochemistry, biology, and all living things which are around us. And rightly, people call it as an element of life. And it has a wonderful ability to bond with itself and and a wide variety of other elements, forming nearly 10 million compounds. It's a mind-boggling number. Now, we very often talked about the greenhouse effect and the emission of carbon dioxide. But without carbon dioxide, I think we cannot grow plants to meet our needs. So it's once again a very, very interesting kind of a thing. And if we try to go slightly deeper into it, we will find that carbon with oxygen and hydrogen forms many groups of compounds which are essential to life, like fatty acids, esters, etc. It has great affinity for bonding with other small atoms, including itself, with multiple bonds. And that is why it is responsible for such a variety of compounds in organic chemistry. Hans Bethe gave us the reason of the energy being produced by sun and stars, and that was again through carbon-nitrogen cycle. It has highest melting and sublimation point. These are also some very interesting aspects of it. And pure carbon is found in very many forms, and these have been synthesized also. For example, diamond is one such form which has been synthesized synthetically. Fullerenes, nanotubes, uh, lancetite, aggregated diamond rods, and the latest addition to this is in fact graphene, which you can see here sitting at the bottom. But if you just try to go above, you will find that the nanotubes are nothing but maybe something which we get after rolling this sheet of graphene itself. And if you try to convert it into a ball, like a football, which we call as a buckyball also, you get what we call the fullerenes, the wonderful big molecules you can call these. The electronic configuration of carbon is very simple. It is 1s2, 2s2, and 2p2, and it has two unpaired electrons in the valence orbital 2p. And sometimes when we look at it, and that comes as a very big surprise to anybody who starts understanding carbon and its compounds, that it can possibly only form two bonds, but that is not the case. We find that the carbon neutral atom is tetravalent, therefore should have four unpaired electrons from which it can form four bonds. And the answer to this question was given by Linus Pauling, a Nobel laureate who got two Nobel Prizes, just like Madame Marie Curie. One was on chemistry, another was for peace. And one of the very interesting books which he wrote, which is like a Bible for chemists, is The Nature of the Chemical Bond itself. And what he did was he proposed a wonderful idea of mixing of two or more atomic orbitals, resulting in new hybridized orbitals. So hybridization is the term which one has to understand and learn if one wants to appreciate whole of organic chemistry or the chemistry of life itself. And that actually meant that it can mix in three geometries, sp, sp2, sp3, and it results in distinct phases of carbon itself. And these are the geometries which are there. And this is the title of that book which I was talking about, The Nature of the Chemical Bond. I think it is a wonderful read. And in the year of celebrating quantum mechanics, I think one should pick it up and read it. It will be very, very interesting. But it was a result of a very interesting paper which Linus Pauling wrote in 1931. And the title of that was The Nature of the Chemical Bond, Application of Results Obtained from the Quantum Mechanics. I would like to underline it and form a theory of paramagnetic susceptibility to the structure of molecules. And the geometry of this is very easily visible to us here. Tetrahedral geometry, trigonal, which is planar. This is three-dimensional. And this is the linear one. And we can always think in terms of sp3, sp2 hybridized orbitals, sp. And this is what normally we see in the books illustrated in the form of these pictures also. And this is a quantum mechanical way of representing these orbitals. Nobody talks about Bohr's orbits. Those were just abandoned by uh, Heisenberg and Schrödinger. And the probability became the way of describing where the electrons are in the orbital itself. So this is from where things started. And I would like to share with you a very interesting letter which was written by A. Noyes to William Foster in 1931 about the importance of the work which was done by Linus Pauling on hybridization. I consider that the field of work in which Dr. Pauling is engaged, namely the study of the chemical bond and of valence, from the standpoint of modern physics, is the most important line of research in theoretical chemistry today. Today, there is complete overlap of what we do in theoretical, say, condensed matter physics or theoretical chemistry. It is very difficult to distinguish between these two. Further, Noyes says, I venture to believe that there is no one in the world who, in the same degree, has chemical background and at the same time has a physical knowledge, mathematical power, and originality required for the holding of handling of this problem. Now, I think it is very interesting to look at the phase diagram of the carbon also. And it is a PT diagram. It typically shows us three things: phase boundaries, phase transitions, and the stability regions. These are so obvious that one can really look at these, that why, say, an allotropic form of carbon called graphite can turn into diamond when we employ at a given temperature a large amount of pressure. And these PT diagrams are essential in various fields, including material science, geology, and engineering, as they help predict the behavior of substances under different conditions. Now, in the case of these typical allotropic forms, I think diamond is the most celebrated one. It has each carbon atom is covalently bonded to 4 other carbon atoms and has a very short bond length of 1.4 angstrom. And this is also a typical number when we talk about covalent bonding itself. And it is a pure sp3 network resulting in a high hardness. And that is why we always use it for cutting purposes also. Now, the precursor to the story which I am sharing with you is basically graphite. And it derives its name from the Greek word called graphein, meaning writing. And it has been used as a writing material since mid-15th century. One of the very interesting parts of it is that it is a layered material in which sheets of hexagonally arranged atoms are stacked and held together via sp2 hybridized orbitals, with each carbon atom in the plane covalently bonded to the 3 others in the plane via strong bonds. So the layers are very strongly bonded carbon atoms. And this continuous network forms a sheet of carbon atom. And these sheets of carbon atoms are stacked together by van der Waals force, which is weak, causing the sheets to rupture, resulting in easy cleaving. And this is where, the discovery of the graphene actually happened. This is a very important landmark in it. Now, if we look at graphite, this is also a highly used material industrially and otherwise also, highly anisotropic solid. stiffness along plane is large and perpendicular to plane, it is weak. Electronically also it is anisotropic because of pi and pi star band overlap. It has metallic conductivity along the plane and semiconductivity perpendicular to the plane. So what a variety of properties graphite has got. So in the last picture, you can see that when we look at the interplanar spacing, it is 3.35 angstrom, which is typical of the regime when van der Waals forces actually operate and act. Whereas along the bonds, the bond length is of the order of 1.42 angstrom, which is quite strong, and it reflects in very many ways later. Now, this is something which is well known, which we may talk of in any typical, say, undergraduate class about its real space structure and how it looks in the reciprocal space. What are the high symmetry points of this, which are very often used when we want to present result of electronic structure calculations also. Now, it's not that this material was not being studied theoretically. It was being studied theoretically. And one of the persons who really looked at it and who lived to see the what you call discovery of graphene was P.R. Wallace. He was a Canadian theoretical physicist. He was a member of the Royal Society of Canada. And let me tell you that he has also been a member of the Indian Academy of Sciences. And in 1946, he published a very interesting paper to look at using tight bonding approximation, the properties of it, particularly anisotropic conductivity, which I mentioned in the beginning. And in Physics Today, in one of the tributes to him in 2006, something was very interestingly mentioned. And I think that even applies today. Our teachers were scarcely aware of relativity and quantum mechanics, which were deemed to be the unique preserve of an esoteric poetry of brilliant, but quite impractical minds. This is something which Wallace described somewhere when he started really looking at quantum mechanics and its applications. And quantum materials are indeed an application of quantum mechanics itself. Now, before we really talk about anything else, there was another very interesting discovery which happened, and this was reported in 1991 by Lizama, a Japanese scientist, who found that carbon nanotubes are also stable materials, and they have some very interesting properties. But there was one thing which was, kept in mind, and that was that maybe it has been made by folding one of the sheets of the graphite itself. Nobody was talking about graphene then. And these carbon nanotubes are also, very interesting. There are three main types: armchair, zigzag, chiral. And the chirality of nanotube refers to the way the carbon atoms are arranged in the nanotube's lattice structure. And it is like, if you take a sheet of paper, you can fold it in number of waves, maybe along one of its lengths, maybe fold along the diagonal itself, and you will find that different chiralities result. And it is described in terms of a pair of integers. And these two actually define what we call as a chiral vector. And we find that this chirality influences many properties of the material itself: electronic properties, mechanical properties. For example, whether a nanotube is metallic or semiconducting depends on the chirality. Armchair nanotube, if you look at different chiralities, like when it is n is equal to 5 or m is equal to 5, it is metallic. Zigzag nanotube, which is, say, typically n is equal to 5 or m is equal to 0, semiconducting. And this chirality can impact nanotube strength, stiffness, and thermal conductivity. Sometimes one gets a feeling in mind that when we try to make even, steel girders, etc., we find that the shapes of these girders define how much strong they are going to be. Maybe that is how, at the microscopic scale, these things are getting reflected here. And here comes a surprise. And I think this surprise is very similar to some surprises which have happened in physics. One which comes to my mind is the surprise which came because of Faraday. He was inspired by Oersted's discovery that around a current carrying conductor, there is always a magnetic field. And he asked an opposite question and he designed an experiment and he was waiting for when will he see the current flowing in the conductor because of a magnetic field which is present there. And then a eureka moment came when he picked up out of frustration the magnet out of that coil and threw it back. And what he saw in the galvanometer was the beginning of what we saw today as a kind of full flow of the generation of electricity and its benefits for the mankind. Now, a very similar thing happened actually after about 15 years of the synthesis of nanotubes. And this happened in UK, in Manchester University. And it happened in a group of condensed matter experimental physicists, Andrei Geim and Novoselov. And Andrei Geim actually had given one of his postgraduate students a very simple task that take this crystal of graphite and try to polish it, and maybe in the process of polishing, you may get a flake out of it, because that stack structure of graphite was enough of an indication that maybe there is a possibility to get it. And this was not actually happening in that particular process. So he went to the market, bought a scotch tape, brought it and gave it to that student, and he said, just put it on top of the graphite polished crystal and peel it off. And to his surprise, when he saw that something has been lifted on the scotch tape itself, and when it was taken under a tunneling electron microscope, they saw that from a three-dimensional crystal of graphite, a one atom layer of graphene has been cleaved or has been pulled off. And I think this was another eureka moment. But why people took so much time to actually taking this kind of initiative to get this two-dimensional crystal itself? And there were three people who I would like to really mention. It is part of the history of the development of the graphene itself. One was Rudolf Perls, another was Landau, and third was Mermin, about whom Professor Das also mentioned. And the conclusion of their work was this, that in two dimensions, there cannot be long-range order and presumably no sharp melting point. And the thermal fluctuations will not let these two-dimensional crystals stable. In literature, this is known as a Wagner-Mermin theorem, and it was actually proved theoretically in the decade of 60s when Cohen was also trying to work out his what you call as this density functional approach itself. Now, Pierre Wallace, what was he saying theoretically? He was talking about all these things which were later found in the properties of the graphene itself while discussing about the tight bonding electronic structure calculations for graphite itself. You can here see the conical shaped band structure, and for a free electrode two-dimensional thing, it is slightly parabolic, but it is completely conical in the case of the graphene which he reported. And what was found actually, when people were still skeptical that maybe something is not that way, the way it should be seen, they found that the crystalline order which is there is quite large, typically of the order of 25 nanometers. And I think these numbers were telling us a proof, or giving us a proof that indeed graphene is a stable two-dimensional crystal itself. In fact, P.R. Wallace and later uh, two other scientists, Solzhenitsyn and Weiss, had concluded that because of symmetry considerations of the honeycomb lattice and by applying tight binding approximation, a two-dimensional model of graphite lattice leads to the point of contact of valence and conduction bands at the corners of the Brillouin zone. And these bands at the contact points have the form of a circular cone in the space of energy E versus A. And this is, very beautifully presented by Professor Das. And now I'm just coming to something which is so easy to understand, which Professor Das also mentioned, was this, that if we take a Dirac equation and convert it into a equation of massless fermions, then this equation, if we try to solve it, and I think it can be done as an undergraduate project, this project today, you will find that the eigenvalues which are there are typically of the kind of, say, plus minus PC. And if you try it, you will be able to see that it is typically of the type h bar modulus of k multiplied by the Fermi velocity itself. Now there is something which is very interesting, and that number was also given by Professor Das in his lecture, that this is quite a large velocity. And maybe what we are seeing in solid state physics or condensed matter physics, a very interesting phenomena, that you have a window now to look at relativistic phenomena in solids at a speed which is much lower than the speed of the light. And maybe it can lead to some understanding of very interesting features of the relativity itself. So this is how a new material, you can call it as definitely a quantum material, was born. It is on an atomic scale, a honeycomb lattice. And there is one thing which is very interesting to note here is that after the discovery of graphene, anybody who was really looking at any of the new elements showing two-dimensional crystal structure, they all have typically this honeycomb lattice. And this is a very interesting hallmark of nature itself, that why this kind of a lattice is going to be a very strong mechanical material also. So it is just one atom thick layer. Imagine it. It's unbelievable. It is a basic structural element of other allotropes, including graphite, charcoal, carbon, nanotubes, and fullerenes. And here you can see that that kind of a symbolism which is there in looking at a fact that maybe this sheet is the basic building block for all the other allotropic forms of carbon in nature itself. Now here, once again, I'm trying to tell that each carbon atom is sp2 hybridized and it is bound to its three neighbors. And by stacking of these layers on top of each other, we can get three-dimensional graphite crystal. It is basically a basic building block. It can be wrapped up into zero-dimensional fullerenes, rolled into one-dimensional nanotubes, or stacked into 3D graphite. So what a wonderful material it is. A single graphite layer with a possibility of leading to so many kinds of formations with exciting electronic properties, mechanical properties, and technological application itself. Graphene is chemically the most reactive form of carbon, and only form of carbon in which each single atom is in exposure for chemical reaction from two sides due to its 2D structure. Carbon atoms at the edge of graphene sheet have special chemical reactivity, So now you are trying to go into the nitty-gritty of the details of the sheet itself. Graphene has the highest ratio of Ag carbon in composition in comparison with similar materials such as carbon nanotubes. And graphene is commonly modified with oxygen and nitrogen containing functional groups. And it burns at low temperatures, that is about 350 degrees Celsius itself. And if you want to describe it in the language of, say, uh, band structure theory, it is a zero overlap semi-metal with both holes and electrons as charge carriers with very high electrical conductivity. Sometimes we use a term ballistic material, because we find that the electrons, when they are moving in it, they are able to move without scattering itself. And that is, when compared to copper, is very, very large, in fact. And on top of that, as was being mentioned, the effective mass of the electrons is now zero. In a way, it is very, very small, one can see. And these are moving with a speed which is 1/100th that of the speed of the light. It has high charge carrier mobility. All those parameters which any, say, uh, uh, technology person would like to see are available in this material itself. Yeah, charge carrier mobility is very large, and in some cases, to the typically of the order of 2 into 10 raised to power 5 centimeters square uh, volts per second have been reported. And uh, this is a typical way of understanding this, that in a case of a semiconductor, how do the valence band and the conduction band are separated, whereas in graphene, these are not separated and there is no band gap. And sometimes, it becomes a kind of a, what you call a typical shortcoming of the graphene because of this band gap itself. And a lot of effort people have put in opening this band gap itself. Typically speaking, you can describe a gap here which is infinitesimal. And sometimes when there is no gap, we are finding that we cannot exploit it as a semiconductor, but we can exploit it otherwise because electrons can move very fast in it. Now, when we look at the mechanical properties of graphene, they are very interesting. And people have actually looked at these properties by making use of atomic force microscopy, in which at the atomic level, we can put stresses into the material and see how it is behaving in terms of its mechanical parameters itself. And it has been found that graphene is harder than diamond and about 300 times harder than steel. And the tensile strength of graphene exceeds 1 terapascal. And it is stretchable up to 20% of its initial length. Now, you tell somebody, say a civil engineer, that these are the properties which are there in graphene, they will start thinking, can we really replace in making of the buildings where we talk about the structures which are having concrete and iron in them, can we replace that iron by the graphene itself and have a very lighter structure, but a very, very strong structure itself? Now, because of its, stretchable properties and folding properties, people feel that mechanically it can lead to new generation of super strong composite materials, and along with very interesting optical properties, we can make flexible displays. But this is something which has already happened. This is not something which has not happened as yet. Also, there is another very interesting property, which is the large thermal conductivity of graphene. And it is much higher than carbon structures as carbon nanotubes, graphite, and diamond at room temperature. And we find that this is being applied nowadays whenever we want to use in particularly the semiconductor industry or making of, say, electronic devices, heat sinks. So now we are not using heat sinks. We are finding that already graphite is being used as a big heat sink which can transport heat away from the device in a very fast time period itself. And a very interesting thing which is again there is that it has got this ballistic thermal conductance which is isotropic, which is same in all directions. So it is not only super fast, but it has got this interesting isotropic property also. And we are using these in a very interesting fashion to make stacking of chips, where we can make use of this uh, in between the layers to transport away the heat which is being generated and can be spread out of this system itself. So what we are finding is that apart from this, we are also able to see that how this mobility people are going to make use of in creating the electronic devices which are the building blocks of, say, modern day computers, which we are using, our mobiles, etc., etc. And we already know that we are able to get graphene-based FETs, which are available in the market now. We have also been looking at spin valve devices with the help of this. Spintronics is also one of the areas in which people are trying to exploit the properties of graphene. And uh, lately, in Professor Das touched upon it in the end that there is a new area which is unfolding called tristronics because of the graphene itself, where if you take two layers of graphene and twist it, you will always find a magical angle at which the properties of this bilayer turns out to be a superconducting material itself. So these are very interesting technological possibilities which are there. Also, it has a wonderful, as we mentioned earlier, that because of its the two-dimensional nature, the bondings which are possible on it, it is a wonderful material for making sensors. And it can sense minute concentrations of certain gases present in the environment itself. Maybe uh, people are using it these days for very many purposes. I think today when we are talking of the COVID also, people were talking about graphene being used as a sensor for detecting the COVID, the viruses itself. Another very interesting area in which this material is being used is in energy storage. And one of the very hot topics these days is how we can have better, say, batteries. And we are finding that instead of the traditional batteries where the chemical reactions are actually involved, the graphene is offering us a very interesting way of creating what we call as supercapacitors. And these supercapacitors can hold large amount of energy with a better performance and efficiency. And these are also being used for developing advanced electrodes that enable faster charging, greater energy density, and longer battery life. Try to look at this in the context of charging of the electric vehicle itself. I think that is the biggest block which is there. And people have found that these graphene enhanced capacitors with their charge discharge cycle exceeding this 10 raised to power 6 are emerging as alternatives that far outpace traditional batteries due to their ability to charge rapidly and deliver bursts of energy itself. So now we are finding that people are slowly and steadily trying to see that can we replace these lithium-ion batteries itself by the graphene supercapacitors and enhance uh, even the life of these batteries by using electrodes made of graphene itself. And we know that as energy demand rises, particularly in electronic vehicles, which are going to be very, very large, typically of the order of 145 million units globally by 2030. These are the areas in which lot of work is going on. Professor Das is an expert in all these things, and these are reliable storage solutions will and this which are bound to grow. They are not going to be uh, small. Now, all these things bring us to some very exciting things which are there happening with graphene, particularly in the context of the smartphone itself. We are talking about touch screens, we are talking about foldable smartphones, we are talking about smart windows, we are talking about wearables, we are talking about maybe transparent materials through which, say, 97% of the light can pass. All these possibilities are getting opened up as a result of this. And one of the major areas in which a lot of progress has been made is in environmental purification itself. And what we notice is that the membranes made of this graphene are being developed for separating salts and impurities from water. So try to imagine, can we make use of this for desalination of ocean water and convert it into clean water with an efficiency which is almost 100%. And this is just something which is beyond what we find in conventional methods itself. Also for capturing carbon dioxide, it has got some wonderful, say, ways of, providing us how we can remove these pollutants from the air itself. So we are also seeing that in the case of biofuel production, in alcoholic beverage industry, people have started making use of the graphene membranes for achieving the results. I think one of the very hot topics on which graphene is being utilized is in harnessing of the photoelectrochemical energy itself. And it's a very, very promising material. Transparent, conductive, and ultra-thin graphene films are being fabricated by the method which made us discover graphene itself. And it has a transparency of more than 70%, which is again a very added advantage. It is also being used as antibacterial material. And for killing bacteria like E. coli, and for hygiene products also. For example, when we are these days using aluminum wraps, maybe in future we are going to make use of graphene wraps for keeping food fresh for longer periods. There is a very interesting possibility which is also being pursued is this, that we can use it to analyze DNA, that is sensing DNAs at a record breaking space. And people are imagining that you can really drill a kind of a hole to make way for the passage of the chemical basis of DNA strand and identifying them. So it's again turning out to be a very interesting area in biomedical field itself. For drug delivery, tissue engineering, particularly for burn injuries, it is very interesting regenerative medicine, which is actually turning out to be. In cancer also, we are finding that it is holding a great potential. And in health market, people are projecting that there will be a growth of 40% rise between 2023 and 2030. And that is where the transformative potential of graphene actually lies. Let me just show you that how people are converting these into materials. We remember that when Edison made his incandescent lamp, his filaments were also made of carbon. Now today we have replicated the same thing by making use of not just, say, graphite for making an incandescent bulb, but using graphene for making the incandescent bulb itself. And that is another very interesting property. Also, we find, and I think some kind of a mention was also made, that there is a huge, what you can call uh, a repository of materials which is actually emerging after the discovery of the graphene itself. Boron nitride, silicene, germanine, phosphorine, borophene, stannine, antimonine. Whenever you find ENE written with anything, you can very well assure yourself that we are talking about a two-dimensional formulation of that particular element itself. And not only that, it has also led to some very interesting what you can call as semi two-dimensional materials like dichalcogenides. Molybdenum disulfide is a very interesting material. And it has an added advantage that it has got a band gap also, which was just missing in the case of graphene. I only mentioned before that we are talking about the twisted graphene bilayer superconductor. And the challenge has been to discover methods to have high yield of graphene for industrial production. From a fundamental discovery of science to technology is the journey of what you call graphene in the last 21 years. And we are making jackets which are very strong. You can imagine these being used by our military personals in the battlefield. These are those, reinforced concrete materials in which it is not the iron bars which are being used, but graphene which is being used here. So as I mentioned earlier also that it is a perfect thermal conductor. It is ballistic thermal conductance it has got, and it is truly a quantum material of 21st century. And graphene has established that two-dimensional crystal is a reality. And it has opened up possibilities to understand unusual electronic properties, not only in itself, but beyond that also. And it has provided a bridge between condensed matter physics and quantum electrodynamics, possibility of studying relativistic effects within non-relativistic realms. And all this happened through a very simple idea of a scotch tape and maybe a pencil which we have been using. And indeed, it is a perfect case of serendipity, whose such profound implications have been dug out from a pencil and an adhesive tape. For preparing this talk, I made use of a number of very interesting articles which were a treat to read, and they are here, which I am sharing with you. There were a number of interesting websites, and they are full of information, and they also give us lead what are the possible things which innovators can use today. There is a lot of talk of innovation around in the country these days for creating new technologies itself. And this is that picture of a bilayer of twisted graphene at a magic angle of 4 degrees, which is very interesting. And with this, I would like to stop here. I hope I am well in time. Thank you for your attention. And I'm back with you.
Thank you, sir. You're very much well in time. We can take a few questions now.
Yeah.
Let me see the chat box.
There is no question in the chat box.
Yes, I have a comment.
Yeah, please.
It was a very simple yet very elegant lecture, and I believe, as you were telling us at the beginning, the laymen like you and the students, young students, will be benefited from it, and they will get impetus to know more about the subject. That is the greatest point of it. I must appreciate it. Thank you very much.
Thank you.
Can I make a comment, Professor Ghosh?
Yes, sir, please.
Yeah. Okay. First of all, it's a very nice overview on both the fundamentals as well as applications of graphene. I mean, one or two things which I would just like to mention. That is, towards the end, you mentioned about the other graphene inspired 2D materials, etc. You mentioned. Now, the thing is, there is one thing that needs to be looked into, and that is whether the material that we are talking about is purely two-dimensional, or there is some kind of an angle that occurs between the in the plane, or there is a kind of a undulation or a I mean, this is something which we have seen that, for example, silicene.
Yeah, buckling is there.
Yeah. So there is always a deviation from pure two-dimensional nature. Another thing is that whenever we are talking about the use of graphene or other graphene-inspired 2D materials for applications, in some cases we are using, the standalone, freestanding graphene. But in many cases, we use graphene as on some substrate.
Yes.
The question is whether the two-dimensional Dirac cone kind of a characteristic remains when we are putting that graphene onto a substrate. Now, this is important because the characteristics of graphene is something which we know is directly related to the Dirac cone characteristics. Now, when you are putting the graphene sheet onto a substrate, depending on whether the interface between the substrate and the graphene is weakly bonded or strongly bonded, that will dictate as to whether the Dirac cone will remain or will vanish. Okay, so these are some of the details that are being investigated extensively by people who are involved in the applications of graphene and also graphene inspired materials for practical applications, which you very nicely elucidated: mechanical properties, thermal properties, electrical properties, gas sensing properties, and so on and so forth. So that is the only comment which I would like to make. Yeah.
Thank you. I just want to mention one thing, sir, and that is for the audience who is here. Dear participants here, let me tell you that in 2010, Professor Das came to our university, and we were actually just trying to have baby steps in doing electronic structure calculations. And we held a 3-week course on electronic structure calculations itself. That was in 2010. And by the time we started moving into the area and looking at various materials, it had been a very exciting journey for us in Himachal Pradesh University itself. And that was inspired by Professor Ghosh. Let me just tell you. Ever since that, we have been in touch. We have been looking at the work which Professor Das group has been doing. And it has been giving us a lot of leads for doing it. And there was in between a transition which happened when we switched over from the strictly two-dimensional materials to those quasi-molybdenum disulfide itself. And in fact, that was inspired by an email which I got from one of my friends in Taiwan. He said, "You are working on this area. Why don't you go and focus on molybdenum disulfide?" And you will laugh at it, what he had written in that mail. He said, "Look, there is a material in which another Nobel Prize is sitting." And I think that was a wonderful, what you may call as inspiration for us to go ahead with this kind of a work. And then one of the publications which we made, that was cited by the Manchester group also. And that was again very satisfying that with these materials, which are small, which can be handled uh, without any big computational resources, can really make us part of the mainstream research in electronic structure calculations. So I want to say thank you very much, Professor Das, for helping us in doing all that.
Thank you so much for all your comments. But indeed, it is true that that we have to make some modest beginnings in anything. And graphene being one of the simplest possible materials, I think this is something which both experimentally, theoretically, and computationally, it can be handled by people even with very modest resources. That much I can tell. And many of the fundamental physics concepts that we know, okay, for example, something which Professor Aluwalia touched, that is, the strength versus ductility. Now, usually from our conventional solid state physics ideas, we know that if the strength increases, the ductility reduces. We know that from the concept of bonding. But graphene is one material where it is possible for us to achieve both strength and ductility in the same material. So these are some of the things that one can really look into from the fundamental point of view of condensed matter physics. So thank you, Professor Aluwalia, for mentioning about our interactions more than 15 years back, and I'm really happy to see how your group has proceeded from there onwards. Thanks a lot for your comments. Yeah.
Thank you very much, sir.
One very mundane question. What is the cost of a typical graphene battery? And how does it compare with lithium battery?
Can I?
Yes, please.
Okay. Professor Ghosh, let me just tell you that the answer to that question is non-trivial. Because there are many things which need to be controlled. For example, the charging and discharging cycles, okay, is something which for a battery is very, very. We are talking about batteries which are rechargeable batteries. So the charging discharging cycles for a battery which is a graphene based battery is something which needs to be checked along with many other properties, which of course graphene, because of its superlative behavior, can yield. But it is something which needs to be probed more deeply before we can come to a stage about the cost. So maybe somebody else can make the comment, but I don't think that we are in a stage to really comment on the cost between a battery which is a lithium-ion battery and a graphene-based battery, because the cost depends on many things. It is the cathode, it is the electrolyte, and things like that. That's a matter of details, and this is not the right forum to talk about it. But all that I can say is that the answer to your question is not very straightforward. We can discuss it later. Yes.
Yeah. In fact, there were few questions also in between in the form of messages which came, and I just would like to talk about that. One mention is that what is the solution for the zero band gap? Is there a solution to that thing as yet or not? I think people have been trying. People have been really trying to bring other materials in graphene and trying to see that can we really open that gap itself. This is what I can mention definitely. There is another question. I have been hearing about graphene and its strength for about 14 years. Are these available on the commercial scale? In fact, in one of the slides, I shown you the pictures of that, concrete, in which instead of steel, people have started using graphene. Try to imagine this material in the light of making bunkers, for example. And let me tell you, whenever these things find a kind of an application in defense, they really rapidly scale up to very big things. And I think we can hear a lot about these things in future. Uh, uh, and there is another question, which is this, that if there is something that threatens us of its uses or some limitation, I think whenever we find that there is a new material, it also comes with lots of limitations. But I mentioned about one application of it, which was usage of graphene sheets for wrapping, say, food itself. That is one area where I think a lot of tests people must have been doing, whether we can use it for different such applications or not. And these are some of the questions which are there. And I hope if you want to ask any further questions, I am available. I am on the IEPT groups, IEPT website, and that you can catch hold of us. Maybe in future you will hear IEPT holding a workshop on electronic circuit calculations also. And we may really request Professor Das also to really help IAPT have this kind of a program over an extended period of about 2 to 3 months, say, in the evenings. And I think that would be a wonderful thing which will happen for IAPT as well as for the stakeholders of physics in research itself. Thank you very much.
Thank you.
So I think we can now conclude this program. I'll request the Secretary of IIPT RC15, Dr. Shinjini Dasgupta, to offer the vote of thanks.
Thank you, sir. Before delivering the formal vote of thanks, may I request Professor P.K. Aluwalia, sir. Sir, one feedback link has been sent to you. Can you please circulate it among all the participants here?
Yeah.
So,
I can share
okay.
it with the participants in my groups. Is it okay?
Okay, sir. Yes, sir. Okay. Okay. Thank you, sir. Okay. So, good evening, everyone. It is my great honor and privilege to deliver the vote of thanks at the conclusion of the second day of the intellectually stimulating and enriching lecture sessions on celebration of 100 years of quantum physics conducted by IIPT 15, organized by them. First and foremost, I extend our deepest gratitude to our respected resource persons, Professor G.P. Das and Professor P.K. Aluwalia, for taking time out of their busy schedule to share such profound insights into the world of quantum physics and quantum materials. Sir, your lectures were not only enlightening us, but have certainly sparked new curiosity in all of us. Your expertise and thoughtful discussions brought depth and perspective to complex quantum phenomena. A heartfelt thanks to Professor C.K. Ghosh for being the voice and rhythm of today's event. Your confident and engaging presence, your smooth transitions, and the way you kept the audience connected throughout the sessions added warmth and structure to the lecture series. We also express our sincere appreciation to the organizers, the volunteers, whose behind the scenes efforts ensured the smooth execution of today's seminar. From meticulous planning to flawless coordination, your dedication is the backbone for this successful event. To all the participants, thank you for your enthusiastic involvement, your questions, and your curiosity. It is your presence that gives such seminars life and meaning. Let us carry forward the inspiration and ideas from today as we continue to explore the mysterious and fascinating world of quantum physics. Thank you once again, and I wish you all a pleasant evening ahead.
So thank you. Thank you, Shinjini. Thank you, Professor Dash and Professor Aluwalia, once again for enlightening us. And thereby we come to the end of the second edition of the webinar series being organized by IIPT RC15. We shall be meeting next on 30th May with yet another pair of talks on that particular day. Till then, good night.
So thank you.
Good night. Good night. Thank you all. Good night.
And thank you, Professor Das, for joining and for your great lecture which we heard today. I was really thrilled. It was great.
Thank you.
In fact, some people are already asking for your lectures PowerPoint presentation itself.
Okay.
But it is going to be available on YouTube, I think.
Professor Anuvalia, this is Achinta Paul.
Yeah.
I have given one or two remarks in your chat box.
Okay.
So kindly have a look at that.
Okay.
Why am I not finding them in the chat box?
It was
directly
it says
sent.
direct message to PK Aluwalia for some reason.
Okay, okay.
Is Professor Aluwalia able to see that? See them?
Yeah, I'm able to see that, yes. Yeah. Achintya Shushmita is there.
Yeah, Achintya Pal actually. Yeah, the name of my laptop is that, so that is why. My name is Achintya.
Achintya Shushmita is the name of the laptop, huh?
Yeah, that is the name of the laptop.
I can see that. Yes.
Yeah.
I'm so thank you very much for making these wonderful and remarks. Thank you very much.
Yeah, and specifically like the layout of your slides, which is very unique. Okay.
I think today, if I may say you, when we are conducting all these lectures, the wisdom of our resource persons is really helping us see very many things around. I think this is for the first time in the history of IAPT itself that such a concentrated set of, lectures with full of knowledge and ideas are being shared. Thanks to 100 years of quantum mechanics, that we grabbed this opportunity to be with our stakeholders spread all across. And it is not that those who were present here in this lecture, they will benefit out of it. I think YouTube channel affords that opportunity for rest of the people who, because of one reason or the other, were not able to attend it. But I think by any standard, the number of participants today was very good, and they were there till the end. I think that is what shows that the way RC15 curated this set of lectures is helping the people and engaging them with the work also.
Sir, this motivates me to look for something, 100 years of something related to physics, important things, for the year 2026. I believe I shall start the search right now.
Yeah, sure. Sure.
So that this momentum can be continued.
Yes. And the best part is that regional councils are coming forward to hold these kinds of programs. That's very encouraging for we who have been given the responsibility of, bringing together the different RCs in the country from east, north, west, south, everywhere. And particularly for me, it has been a great learning experience with the members in our IAPT community and beyond that also. So thank you. Can we really wind up now and end the session? Mr. Ghosh, may I do that now?
Yes, please. Yes, please.
Thank you.